You can review content from Crash Course Organic Chemistry with the Crash Course app, available now for Android and iOS devices.
Hi, I'm Deboki Chakravarti, and welcome to Crash Course Organic Chemistry. Lots of foods are bright reds and pinks, from the natural hues of a raspberry or a beet to the amped up colors of pepperoni, red velvet cake, or pretty much any cherry-flavored candy. Food manufacturers know that bright colors catch our eye in a supermarket aisle. So they often give packaged foods with long shelf lives a little bit of psychological razzle-dazzle. Sometimes this is achieved with dyes, but you might also have seen the food additive sodium nitrite on the ingredients list of cured meats like salami or ham. Sodium nitrite gives them a bright pink-red color by acting as a substitute for oxygen and binding to myoglobin in the meat. It also prevents the growth of some really dangerous bacteria. We don't have time to get into that here, but trust me, you don't want to be eating botulinum toxin. Those additives come from chemistry, of course, and are involved in some interesting non-food related reactions too. Let's take a closer look. When sodium nitrite is mixed with a cold mineral acid, hydrochloric acid for example, it forms nitrous acid, HNO2. It's often called HONO by chemists because that's how the molecule is arranged. Nitrous acid sounds a little bit like nitric acid, but they're not the same. Nitrous acid has one fewer oxygen atom. Last episode we talked about amines, and nitrous acid can do some pretty interesting reactions with them. In fact, these reactions can be used to distinguish between primary, secondary, and tertiary molecules. With primary amines, a cold acidic solution of nitrous acid forms nitrogen gas, so we see fizzing. With secondary amines, we get an oily layer of really toxic nitrosamine, which is why this test may not be the first choice these days. And with tertiary amines, a soluble salt forms, so we see a clear solution. But let's focus on primary amines right now because the product of this reaction is neat. It's an organic compound called a diazonium salt, which has a nitrogen triple bond. Let's take a look at the mechanism. First, the nitrite ion picks up a proton to form nitrous acid. If there's plenty of acid present, it picks up another proton and then falls apart to give us water and a nitrosyl cation, NO+, which we can think of as nitric oxide minus 1 electron. So overall, in acidic conditions, nitrous acid dehydrates to form a nitrosyl cation. The nitrosyl cation is a fairly weak, resonance-stabilized electrophile. The lone pair on the nitrogen of a primary amine readily attacks it, which forms a new nitrogen-nitrogen bond. Next, there are 2 proton transfers from nitrogen to the oxygen, and the electrons shuffle around so that we end up with a nitrogen double bond. And finally, that super stable nitrogen triple bond forms, and water is eliminated. We have our diazonium salt. But diazonium salts are unstable, particularly alkyldiazonium salts. Nitrogen gas is a fabulous leaving group thanks to its hugely stable triple bond, so it might fizz away and leave behind a reactive carbocation. As we know, carbocations can be pretty useful. In theory, we can make all sorts of things, like haloalkanes. But in practice, these reactions can be difficult to control. If we have a diazonium salt in the presence of water, for example, we get products of addition and elimination, with and without rearrangement. The technical term for this is a big freaking mess. There is one not as chaotic reaction worth remembering. If the starting amine is a 1-aminomethyl cycloalkanol, besides being a mouthful, it's a potential reactant in the Tikhonov-Demianov rearrangement. Named after Mark Tikhonov and Nikolai Demianov, the French and Russian chemists who worked on the mechanism, this rearrangement starts when the cyclic amino alcohol reacts with nitrous acid to form the diazonium salt. Then, with a little push from oxygen, this carbon-carbon bond migrates, kicking out nitrogen gas to give a cyclic ketone, larger by 1 carbon. Pretty useful. Now, so far I've been talking about alkyldiazonium salts, but aryldiazonium salts, which have aromatic rings, are more stable. When there's a nucleophile, a substitution reaction can replace the nitrogen group in aryldiazonium salts. Some sources say it could be an SN1 mechanism, which, as we learned back in episode 20, doesn't work well with sp2 hybridized carbon atoms. They argue nitrogen gas is such a good leaving group that the aryl carbocation can actually form. But most sources say the mechanism involves radicals. So it's complicated, and there's still more organic chemistry to discover. Anyway, we can add all kinds of nucleophiles, like halide ions, hydroxide, or cyanide, to make lots of different substituted benzenes. In fact, nitration, then reduction, then diazotization, and finally substitution is an extremely important sequence in aromatic chemistry. For example, let's try to come up with a synthesis of meta-dichlorobenzene from plain old benzene. As you can see, the two chlorine groups are meta to one another, but chlorine is ortho-para-directing. So if we try to just add two chlorine groups directly, they'd end up in the wrong position relative to each other. We need to do something clever here. Let's use that sequence I just mentioned. The first step is nitration, which is useful because the nitro group is meta-directing. So once we have that in place, we can get the chlorine where we want it. Next, we reduce the nitro group to an amine. Then, the diazotization we just learned forms an aryldiazonium salt. And finally, substitution replaces the amine group with the second chlorine. Neat, right? There's one more reaction of aryldiazonium salts we need to mention, diazo-coupling, which is how we make azo dyes. The diazonium salt is a fairly weak nucleophile, so we need an electron-rich aromatic compound to react. NN-dimethylanilin is one option. Azo is an extremely handy Scrabble word, but more than that, you've probably eaten these compounds at some point. Lots of azo dyes are used as food colorings, and the product of this particular reaction is a yellow dye called methyl yellow that is used to color plastics. Their basic structure is two benzene rings connected by a nitrogen-nitrogen double bond. Because of this, they have extended conjugation and can absorb visible light. Azo dyes tend to absorb light in the blue and green region of the visible spectrum, meaning that it's the red, orange, and yellow wavelengths of light that make it to our eyeballs. For example, there's Ponceau 4R, which also goes by lots of other names, like E124. Ponceau is from the Old French for poppy-colored, so this compound is bright red. This azo dye is stable to light and heat, which is good news if you're trying to make red velvet cake. Although it does fade in the presence of some food acids. Now, since we're talking about aromatic compounds and the reactions they can do, let's quickly recap the electrophilic aromatic substitution reactions we first met in episode 37. Electrons in the pi system attack an incoming electrophile, and we form an electron-deficient intermediate. Since a fully conjugated pi system is super stable, the electrons in the carbon-hydrogen bond in the intermediate hop back to reform it. Then the proton is kicked out, and we end up with a substituted benzene ring. Now, in that mechanism, the ring is nucleophilic. It's a big conjugated pi system stuffed with yummy electrons, right? How could it be anything but an electron donor? Well, turns out that nucleophilic aromatic substitution is a thing too. A benzene ring can behave as an electrophile in specific circumstances. First, we need a strongly electron-withdrawing group or two, which we write as EWG on the ring. Second, the ring needs to have a good leaving group, and that leaving group needs to be ortho or para to the EWG. Quick review from episode 38. If the atom directly bonded to the ring is connected to an atom more electronegative than itself, the substituent is electron withdrawing, meta-directing, and deactivating. We learned that for electrophilic aromatic substitution reactions, an EWG is deactivating. So this means for nucleophilic aromatic substitutions, an EWG speeds up the reaction. It makes sense if you think about it, because we're trying to get the ring to accept an electron pair, so reducing electron density is the way to go. Let's look at how this mechanism works with an example. For instance, a nitro group is a good electron withdrawing group. And if we consider the resonance structures here, we see something important. The ortho and para positions are partially positive, which is perfect for nucleophilic attack. Of course, to do a substitution reaction, we also need a good leaving group, like a halogen. We'll use chlorine. For our strong base and good nucleophile, we'll use sodium methoxide. It attacks at the para position, which is already partially positive thanks to the nitro group, and made more so by the electronegative chlorine. The pi electrons are pushed around, and we form a non-aromatic intermediate. But like before, the pi system is super stable, so it's restored. The chlorine gets pushed out, and we've substituted a methoxy group onto the ring. If we think about this in terms of substitution reactions for a moment, it's not SN1 because we're not forming a carbocation. And it's not SN2 either because the nucleophile would have to go through the ring, which can't happen. So this is something different. You might see it called SNAR, which stands for Substitution Nucleophilic Aromatic. You might have guessed from how much I'm emphasizing the nucleophilic in nucleophilic aromatic substitution, but it's super important that we don't mix this mechanism up with electrophilic substitution reactions, even if they look kind of similar at first. Remember, in SNAR, the aromatic ring is acting as an electron acceptor, whereas in EAS, the aromatic ring is an electron donor. Okay, so let's put all of this information together. Let's say we're starting with a plain old benzene ring and want to make the starting compound from that last problem. A benzene ring with a chlorine para to a nitro group. How can we get both groups substituted onto the ring in the right places? Thinking about how these groups direct, we know that chlorine is ortho-para directing, while the nitro group is meta-directing. So if we put the nitro group on first, we're going to have a very hard time getting the chlorine where we want it. Okay, that means we need to do the chlorine first. So first we do electrophilic aromatic substitution using an iron catalyst. Next, it's time for nitration, using concentrated sulfuric and nitric acids. It's likely we'll get a mixture of ortho and our desired para substituted products, but we can separate those. And we've made the aromatic compound that can undergo nucleophilic aromatic substitution to get the molecule we want. Okay, let's do one more problem for good luck. This time, we'll start with chlorobenzene and make 4-cyanophenol, which is used as an antiseptic, disinfectant, and an important intermediate in other reactions. So looking at what needs to happen, we can substitute that chlorine to make a phenol, and we can get the nitrile group on via nitration and formation of a diazonium salt. But what shall we do first? This time, it's not about how these groups direct, even though we know chlorine is ortho-para directing by now. Instead, we need to focus on whether we're creating a more electron-rich or electron-deficient ring at each step. Remember that for nucleophilic aromatic substitution, we need an electron-withdrawing group. A nitrile group is electron-withdrawing, but the phenol pushes electrons into the ring, so the phenol needs to come last. First up, nitration to get a nitro group on our ring. Next, we can reduce that group with some hydrogen and a palladium catalyst to form an amine. Then it's diazotization and nucleophilic substitution to get the nitrile in place. Like I said, this nitrile is electron withdrawing, which is exactly what we need for a nucleophilic aromatic substitution reaction. All we really need to do is make sure the right nucleophile, hydroxide, is in place. And we're done. Not just with this problem, but we're done with aromatic reactions and the whole episode. We just learned that nitrous acid reacts with primary amines to form diazonium salts, alkyldiazonium salts are very unstable, aryldiazonium salts can be used to make substituted benzenes, and nucleophilic aromatic substitutions are possible if we have a good EWG and leaving group. Next time, we'll start wrapping up everything we've learned in this course by looking at biochemistry, the chemistry of life. Until next time, thanks for watching this episode of Crash Course Organic Chemistry. If you want to help keep all Crash Course free for everybody forever, you can join our community on Patreon.